Alright, this is the second part of ideal gas equations. So what is ideal gas equation? Ideal gas equation is called PV equal to nRT or PV equal to nKT. This is the most important equations in this chapter. PV equal to nRT and PV equal to nKT. All the symbol in this page, I already explained all this symbol use, all this quantity I use. What's the symbol, what's the unit, I already explained in the previous first part videos. So I hope you watch the first video first before you come into the second part of the videos. Okay, for example, like this N, first of all, the P, pressure, must use Pascal, volume must use meter cube, temperature must use Kelvin, the mass you must use kilogram. Mass you must use kilogram. Now, so small n is called the number of mole. So if the question gives you number of mole, you use nRT. Capital N is called the total number of gas molecules. So I already explained here. Small n, where is the small n? Small n is the number of mole. Capital N is the total number of all gas molecules. Capital N, total number of all gas molecules. So if the question gives you the total number of all gas molecules, you use nKT. And out of this equation, P equal to nRT, you come up with many laws. We have Boyle's law, Charles' law, Gay-Lussac or pressure law, and in the end, the ideal gas equations. Okay, what is Boyle's law? Boyle's law is P1 V1 equal to P2 V2. This one you have initial and final. Initial and final, or between situation 1, situation 2, how the pressure and volume changes. Okay, if you increase the pressure, the volume will decrease. This one the temperature must be constant. This is very important. Temperature must be constant. For Charles' law, it is V1 over T1 equal to V2 over T2. That means you increase the temperature, the volume will also increase. So this one, pressure must be constant. And then you have Gay-Lussac or pressure law is P1 over T1 equal to P2 over T2. So this one, volume must be constant. Okay, volume must be constant. And then at last you have ideal gas equations. Let's say you have none constant, temperature change, pressure also change, volume also change, everything change. Then you use the ideal gas equation. P1 V1 over T1 equal to P2 V2 over T2. That means all the pressure, volume, temperature all change, none constant. And then you use this equation, ideal gas equation. If one of it is constant, so identify which one is constant, and then you use the laws accordingly. Either it's Boyle's law, Charles' law, or pressure law. For Boyle's law, pressure is inversely proportional with volume. For Charles' law, volume is proportional with temperature. For pressure law, the pressure is proportional to temperature. Okay, so you must identify which one is constant, and then only you will use the correct law. Okay, all these formula actually come from PV equal to nRT. They come from this equation. You see, all these equation all come from PV equal to nRT. But all these four equations, actually the condition is the number of mole or number of molecule must be constant. The number of mole or number of molecule must be constant. Okay, actually, how do we get nRT and how do we get nKT? Okay, these two formula actually come from, if you substitute R equal to K and A, and then the number of mole, you substitute with this formula, the total number of molecule divided by Avogadro constant. You substitute these two equations into P equal to nRT, you will surely get P equal to nKT. Substitute these two equations into P equal to nRT, you get PV equal to nKT. So these two formula is the same, just that this one use number of mole, This one use total molecules. And then, yeah, and then other than these two equations, PV nRT, PV nKT, we also have PV equal to 1 over 3 nmv square. So you also can change, no need to use nRT or nKT, you can also use 1 over 3 nmv square. This is a root mean square speed, yeah, square. And then this one, VRMS square, you can change to mean square speed. Just like what I have explained in the first part of videos, the VRMS square is also mean square speed. So you can write like this, or also can write like this. These two means the same thing, mean square speed. How to get this? Actually, this one we get from the root mean square speed. I already explained in the first video. Square both sides, you square both sides, you get this. You square both sides for the root mean square speed, you will get the mean square speed. Okay. So VRMS square also equal to mean square speed. Yeah. Now, let's go back to this one. Okay. So that's why VRMS square is also mean square speed. You can write like this, or you can also write like this. And then we have you notice here, this one is the big capital N, which is the total gas molecule. Small m is the mass of one gas molecule. Mass, this is the total number of all gas molecules, multiply with the mass of one gas molecule. So what you get that? Still remember this one? The total molecules, capital N, multiplied by mass of one gas molecule, capital N multiplied by mass of one gas molecule, you get the total mass of gas. Okay? So total capital N, the total gas molecule multiplied mass of one gas molecule, you get the total mass. So total mass of gas, divided by volume of the whole gas, get the density of gas. This is the density of gas. So that means this volume here, okay, the volume over here, okay, if you transfer below here, okay, you transfer it below here, means that means this volume, you transfer this volume to here. Okay, this volume transferred here. So Nm over V, you get the density. This equation. So pressure is also 1 over 3 density VRMS square. So there are 5 popular formula here you need to use. P equal to nRT, P equal to nKT, PV equal to 1 over 3 nmv square, or mean square, and also P equal to 1 over 3 density VRMS square. Okay, and make sure for all these equations, all the temperature here, all this temperature and T1, T2, all this temperature, all the temperature here, you must use the absolute temperature, Kelvin. You must, from degree Celsius, you must change to Kelvin, because all these refer to a single temperature. Yeah, they refer to the single temperature. All this you must use Kelvin. If you use degree Celsius, then you will get wrong answer. Okay, in this chapter. Yeah, so even the T1, T2, all this you must use Kelvin. When do we use degree Celsius? In the previous chapter, we learned about heat conduction and thermal conduction. You learned about the change in temperature, isn't it? The change in heat conduction and the thermal expansion. They're concerned about change in temperature or temperature difference. Yeah, temperature difference, which is the final temperature minus initial temperature. So this one involves double temperature, two temperature, change in temperature. So this one you can maintain as degree Celsius or Kelvin. So either one accepted. Yeah. You use degree Celsius, also you get correct answer. Because this value they involve two temperature, so you can use either one. But yeah, that means this one, the previous chapter you no need to change to Kelvin. But for this chapter, you must change to Kelvin. Like this one, even this one got change in temperature, but this one takes the value of single temperature and single temperature. The T1 single temperature, T2 single temperature. T1 single temperature, T2 single temperature. So this one must be in Kelvin, T1 must be in Kelvin, T2 must be in Kelvin. This one takes single temperature. It does not take the change in temperature, understand? For change in temperature, you can use either one, degree Celsius or Kelvin. The change in temperature, you can use either one. But for single temperature, you must use Kelvin. Understand? Yeah. So yeah, that's it for, I think, for the second part of the videos. So stay tuned for the next subtopic. Okay, see you.